The deal here is that we can cover material that you're having a problem with, like if there's a homework issue or something like that, or something you didn't understand from the class, or if you want to see me do something with SPSS or demo something, we can do that. But I also, for tonight, there's one thing I want to cover that we really didn't have time for, and it's something that I think is going to be valuable to you in the long run to understand, but that I'm not going to wind up testing you on. Since we're doing it as part of the voluntary part of this thing, you're not going to wind up seeing it on like a test or anything like that. Okay, and that's like standardization. In our case, we're going to do a demonstration called age adjustments. Have you guys ever heard of that? Like age adjustment or standardization? It's come up, right? Have you ever done it yourself though? Okay, good. Then what we're going to do is something new. So I got you guys online. Have you ever done a standardization of data or an age adjustment for data? They're shy. Okay. Oh, good. Okay, so we have some, at least one person that's done this before. Okay, so I'm going to get started. And first, I'm going to show you basically a reason why we might even entertain doing this. In other words, why are we modifying? Why are we monkeying with the data that we might be collecting during a study or something like that? Well, first of all, I've accumulated a bunch of data here about the death rates, number of deaths in a specific year, the mortality from cardiovascular disease in New York. And it's divided up into females and males. I just want to show you where this came from. Because later on in the semester, you're going to be looking for sources for data from your projects and so on and so forth. I want to see if I can't find the spot where this came from so that you guys can see it later on. New York City. Let's see. Vital statistics. If I can't find it quickly. New York City vital statistics, and there's also something called EpiQuery, which we'll be talking about in a while also. Let me see if I can't get the summary of vital statistics going back to 1991. Nope, that's not what I want. I want the actual report. Here's a report for 2014. Okay, so you saw this graph before, this on the cover page. This is the morbidity or mortality report for the city of New York. Vital statistics. Vital means living, right? Life statistics, life and death. Okay, and we saw this graph as part of Levi's lecture last week and a half ago or so, right? And you can see that this is the mortality rate for all of these different years, starting going back about to 1800 in New York City. And you can actually see peaks and valleys here that are associated with significant events that occurred during that period of time, like for instance, cholera outbreaks and smallpox. And you've noticed, the other thing you notice is that over the years, particularly lately, the mortality rate has declined. The number of people dying per 100,000 people in New York City has declined. And in fact, if you look really close, I have a little inset there, where if you look really close over the last 10 years or so, there's a blip there that they kind of isolate. And that's 9/11. There were 3,000 people that died in 9/11. So that actually had an impact on reversed the declining mortality rate in New York for that year, for that particular year. So you can actually see the impact of all these different events. But at any rate, the real reason for this document is that we can go through this document and you will have information in here on all sorts of statistics about death, causes of death, ages of premature death, for instance, reasons for premature death, and also just standard statistics on what exactly was causing mortality in New York City by age rate, by group. And for mortality, I want to get to the main core of this. And let's see, pregnancy outcomes. Hope I didn't pass it. Pollution characteristics. I should have gone to the index, right? So I didn't blow past it. Okay. Premature. Well, I'm going to use this chart. It's actually premature death, but there is another one that has all the age ranges. So if we look at this, this tells us that that during 2014, the primary cause of premature death, like less than 65 years old, was malignant neoplasm, which is cancer. Okay, and this is the number of deaths, and this is the number of them that were males, that were females, and so on and so forth, or percentages. Actually, I have percentages here. I want to find the actual numbers so you know actually where this came from. Leading causes of death. Here we go. So from age, let's see, for all ages, we have this block up here, but for infants less than 1 year old, these are the leading causes of death, and we have the exact number of deaths that are involved here. 116 from short gestation, low birth weight, respiratory distress, so on and so forth. Then from 1 to 14, we have deaths. Leading cause was cancer. From 15 to 24, leading cause was assaults, homicides, and accidents. From 25 to 34, poisoning by drug overdoses, leading cause of death in New York City for people in that age range. And we actually have numbers about how many deaths there were. If I look at a specific cause, though, cardiovascular disease, if I look at that, diseases of the heart and cerebrovascular disease, there were 14 deaths in this age range, right, in New York City. Of those 14, let's see, male and female, of those 14, looks like 6 of them were male and the remaining were female, and so on. So I could go by age group here and add up all the deaths and find by cause the number of people that died from a specific cause among the top 10 for each age group. And that's what's happened here. That's how this data has been accumulated. Okay, so in other words, I left out one category here. Between 24 and 44 years of age, 144 females died in New York from cardiovascular disease, and 277 males died from cardiovascular disease. So I'm going to calculate now something called a crude mortality rate. Basically, it's just how many people died from that cause out of the total number of people that are in New York City. So I'm going to calculate it for two groups. I'm going to calculate it for males and for females. So conventional wisdom, who is more likely to die from cardiovascular disease, males or females? Males. Everybody agree, males? Right? Sounds right. Right. I mean, that's usually what you would associate with cardiovascular disease, males rather than females. Okay, so let's take a look at that. In this particular year, I forget what year it was. Let's calculate how many people actually died. Let's see, we got I'm going to do this in here. So we had 12,627 females out of a total population within these age groups of 2,854,000. So what rate did they die at? They died at the rate of 0.004. In other words, 0.4% of them died in that given year. Okay, it's kind of funky working with that number. So I'm going to take that number and I'm going to multiply it. I can either do this on top. I'm going to do this by putting it into parentheses first, and then multiplying by 100,000. Right. So the probability of an individual dying from cardiovascular disease, a female, was 0.4%, 0.004 out of 1. Right. That's the way we would describe that proportion. That's the proportion. Okay, so I'm going to multiply that by 100,000. So I'm looking at the rate that would be the cardiovascular deaths per 100,000 females. I'm going to enter, and it's 442 women per 100,000 population died in New York City. Females died in New York City from cardiovascular disease. Now I'm going to do males. Equals, so we have this number of deaths. It's a smaller population, though, over this, parentheses, times 100,000. I'm going to hit enter, and what do we got? 413. So what does that tell you? The rate of mortality for females in New York City is higher than the rate of mortality for males. Okay, so now we have a problem with that, right? Somehow or other, we're not getting what we would expect, or in fact, what the reality is in terms of the risk of cardiovascular disease between the genders. Okay, so let's take a closer look at that data. Okay, I have this data isolated over here in a format where I could actually see it for each group. This is the number of males for each group. This is the number of females. This is actually just the population, the total of males and females in each one of these different age ranges that we were looking at. Now I changed those down here to percentages. In this particular year, within the population, the age groups that we took here, 48% of them were in 25 to 44, 32% were in that range, and so on and so forth. So I'm going to take this and I'm going to create a graph out of it. Okay, let me go up to charts, column. Okay.
SPSS, right?
I'm using Excel right now. Yep, using Excel right now. So let's see what happened here. Let's see. If I look here, let's see. It looks like well, you know what I should have done here. Let me hang on a second. I don't think I didn't. Oops. I didn't include the titles. I don't think male and female. Let me just do this again so I can get the columns identified. I'm going to go into charts, columns. Okay, and now it identifies the blue or male and the red or female. Okay, so let's see. Okay, so, it looks not too different when I look at each of these groups. 45 to 50, 64, roughly about the same percentage. 65, and this is population, this is the number of deaths. The population of New York has more females than males in the age range of 25 to 44. I'm looking in this room and I figure most of you guys know that already, right? So especially good males, right? We don't have a dearth of those in that age range. Okay, now from 45 to 64, it's roughly the same number, so same proportion of the population is male and female. Once we start to get up into 65 to 84, there's more females than there are males in New York City. And once we get up to 85 and older, you can't see it too well there because the scale is compressed so much, but there are 3 times as many females that are over 85 years old as there are males. Excuse me? Oh, I got it reversed. You're right. You know what happened there? I reversed the columns. Yeah, that should be the other way around. There's 3 times as many females. How do I do that? Yeah, hang on a second. Yeah, you know what? Because the columns over here are female, left and right. Female. I reversed the left and right there. Now, one of the nice things about Excel is that chart and the cells I made it from are linked. So as soon as I fix the chart, it fixes. As soon as I fix the table, it fixes the chart as well. So there are 3 times as many females as there are. Actually, 3 times as many females as there are males that are over 85 years old. Who has the highest risk? What age group has the highest risk of death from cardiovascular disease? Well, what age, right? What age group? The older you get, the more likely you are to die from cardiovascular disease. In fact, if you look at the number of deaths, right? Take a look at this. Very few deaths in the first group, somewhat more, but the highest rates of mortality and the highest number of deaths, look, 6,000. That's only out of 87,000 people. So the rate of mortality really goes up quite a bit as you get older. The female population, according to this, it looks like the female population overall is an older group than males. Males tend to die off younger from many causes, right? So there are fewer older males than there are older females. So they skew our data. They make it look like females have a higher risk of mortality from cardiovascular disease. But really, that higher risk is really due to the fact that they have much higher older population. So we need to find a way of adjusting for that factor, for standardizing the data, for doing an age adjustment. What we're doing in this case is we're really removing a confounder. The difference in the age population here is a confounder. It confounds our examination of the other variables here. Okay, so let's do that. Let's take a look at what we can do about that. First thing I'm going to do is I'm going to calculate the age-specific mortality rate for each one of these age groups for male and female. Okay, so remember, you guys will be able to watch this again, slow it down, and watch it again later on. When we put the video up. So I'm going to go in here and I'm going to calculate the age-specific death rate for each of these groups for females. So in this column, that's going to be equal to total the number of females that died in that group was let's see, 146 females out of let's see, I think I messed up. Oh yeah, 146 females out of 1.3 million. Okay. That's going to be equal to, that's our rate of mortality within that group. And I'm going to copy that down. Okay, the only thing, in order to copy that down, well, actually, I can just go ahead and copy it down, I think, because the cells are joining one another. So I'm going to copy it down. And those are the rates of mortality within each one of those groups. Notice that in the beginning, it's 100th of 1% in the youngest group, and then it goes up to almost 7% of the population over 85 dies from cardiovascular disease that year. I'm going to do the same thing for males. This is going to be equal to the number of males that died over the number of males within that age group. So it's the age-specific mortality rate. So I'm going to copy that down. Whoops. Didn't cooperate with me that first try. Good. There we go. Okay. So we're going to take a look at that now. Okay, so now notice that the rates within the age groups, well, males are a little bit higher in almost all of these age groups, aren't they? Interesting. So now we're going to use those age-specific mortality rates, which we kind of did already because we looked at the rate at which people were dying in each one of these different categories. We're going to use those now, but instead of applying those rates that males and females die within the age group to two different populations, male population and female population, we're going to apply both those rates to the same population. Okay, so we can get rid of that fact that the two populations, male and female, have different age distributions. So what can I use as a single standard population as a reference, do you think? Any suggestions? It could really be anything. I mean, I could just say, let's take a population that has 100,000 people in each age group. That's kind of artificial to do that, though. So maybe what I'll do is I'll add the males and females together. So I look at them as one block and apply the age-specific rates to that same population, as if everybody were the same gender, but we're going to use different rates of mortality. Okay, so that's what I'm going to do. Each one of these columns next to it is the sum of the number of women and number of men living in New York during that year. Okay, and this is the rate at which they died. So now I want to know, well, how many people would I expect, how many females would I expect to die if the female population was 2.6 million and they died at the rate that I calculated? So that's going to be equal to the number of people times the rate they die at. So we're going to expect 283 groups with deaths within that group. I'm going to do the same population for all the other groups.
This is age standardization?
Yeah, this is age standardization. Okay, so now I'm going to add those all up. Okay, so based on the rate that women die at in each one of these age-specific groups, if this were the population of females, this is how many women I would expect to die. And that would be 1,952. I'm going to do the same thing with males now. How many males would I expect to die if there were 2.6 million males in that age group? So it's going to be equal to the rate at which males die times the size of that population. Okay, and I'm going to do the same thing for 4564. I'm going to do it by just copying the formula down. Okay, and now I'm going to add this up. And I'll see how many males died. Whoops, how many males I would have expected to die. I forgot to put equal sign in there. Okay, do this again. And this is the number of males that would expect to die in that same population if they were all dying at the rate that males die within each age group. Okay, so now let's take a look at what the age-adjusted female mortality rate is. It's going to be the number of women that died in that age group over the total population of women, because they're putting together a kind of a fake population of women. It's really the sum of males and females, times 100,000, just so I can get that number per 100,000. And it's 371. Let's take a look at what happens with males. Equal to the number of males that would have died, that we would have expected to die, over that same population. Now, not a different population, but the same population. Their rate applied to the same population as females, times 100,000. And what do we see? Given that if the population distribution was the same, we would see males dying at 1.5 or more times the rate that females are dying at from cardiovascular disease. So this represents really the reality here, right? That males are more susceptible to death from cardiovascular disease. The only reason that it seemed like when we looked at the crude numbers without adjustment, that it appeared that females were dying at a higher rate than males were, was because there's a larger, older population of females. And older people have much more risk for cardiovascular disease than younger people. Okay, makes sense? Yeah.
I got the basic functions.
Yeah.
But I think maybe because I walked in late, I don't understand like the flow of what just happened.
Okay. This is going to be recorded on a video. So like later on, you'll be able to go back over this. But you get the idea. What we're dealing with is that there's very frequently going to be confounders. Like age is a frequent confounder. If we're trying to compare women to men, and the population of women is older on the average than men are, well, if we have a disease that tends to be prevalent at an older age, then even though men might be more susceptible, right, it appears that women are dying at a faster rate simply because there are more older women, and the rate at which older people get it is so much higher. What can you think of that would have a similar confounding factor where age is concerned, where you might, if you're doing statistics, you might be prone to want to do age adjustment as well? What other disease is more prevalent when you're old than when you're young? Excuse me, diabetes? Okay, yeah. In fact, I think diabetes really just only starts to show up on that top 10 causes of mortality until you get a little bit older. How about another one, right, that everybody dies from at some age, right? How about cancer, right? Cancer, right? So you might see the same effect from cancer. In fact, I'm going to post later on, I'll post a spreadsheet that has some of these basic numbers for the mortality rates in Florida and Alaska from cardiovascular disease. Where would you say that people die at a higher rate from cancer? What's that? Florida, right? And you would say Florida, right? Why would you say Florida? Because is there something in the environment that's causing them to die from a higher rate in Florida? No, they're just old, right? The population of Florida is so old that if you calculated their mortality rate from cancer, it's much higher than the average rate in Alaska, right? So, but now, let's say you want to examine that more closely and see if there really is an environmental problem that will cause people to die at a higher rate than as people in Alaska. Alaska is a very young population, right? You got to be young or you can't live up there. It's like brutally, it's like the environment's brutal, right? Most of the jobs there require relatively young, fit people. So I'll give you some data on that. So you can have, from the raw data, you'll be able to calculate the crude mortality rate for Alaska and for Florida due to cancer. And then you can do your age adjustment, because you'll have the age-specific rates, do your age adjustment and do the same calculation after adjustment and see if there's really a difference in the mortality rate from cancer. Okay, and I'm thinking, well, gee, if there's nothing environmentally that would cause a difference between those two groups, well, gee, I would expect that when I do my adjustment, the rates are going to be very similar. But I'll leave that up to you guys to give that a try. Okay? Okay, so good. So that's age adjustment. This method is called direct adjustment. There's another method that's called indirect adjustment. I'm going to post an article that will have a description of how to do indirect adjustment, but you don't have to worry about that. In fact, this is for demonstration purposes. I'm not going to wind up testing you on this because since I'm doing it as part of the voluntary session here, like in class session, I'm not going to expect that people that miss this or something like that are going to have to do it. But it's valuable to know this stuff because you're going to see instances where, for instance, later on in the semester, we're going to look at data where you're going to make a choice. Do I want to work with the raw data or do I want to work with adjusted data? And you're going to want to know how it was adjusted and whether it was standardized, how it was standardized. Okay, but this is a demonstration of standardizing data so that we remove some factor that confounds your understanding of the variables that you're interested in. Okay, doke. Okay, good. How about how have we been doing on homework and stuff like that? You guys started that yet?
Questions?
Yeah, sure. Questions. Good. Let's talk.
How do you migrate data from the Excel?
Okay, good question. Let me just check online, see how these guys are doing here. It says level impact, actual confounding. Justin, right. Good idea. Yes. That's correct, Justin. But the real reason we're doing this because we want to remove a confounding factor, the fact that the age distribution of the two populations is different. And this is not on your homework assignment, and I'm gonna post another spreadsheet that has data for cancer in Alaska and in Florida, mortality rates from cancer in Alaska and Florida, and you can take that spreadsheet and do your own age adjustment, see what kind of results that you get. Calculate the crude mortality rate, then calculate the adjusted mortality rate. So it's only for this live session. And since the live session is a voluntary session, I'm not going to wind up putting it in the homework, a graded homework assignment. It'll just be an exercise. And also, I won't expect you to have to do it on a test or anything like that. Okay, good. So let's talk about migrating data back and forth. Let's open up SPSS because I think a lot of you guys are just starting to get into that. Okay, I'll start it up on my machine. How many of you guys here have already downloaded and installed it? Okay, good. How many of you guys are using it through the virtual desktop? One person. Anybody try it on the virtual desktop and not succeed in getting it to work? Yeah, I have the same problem. It doesn't like my login for some reason. Yeah. Okay, just so you guys that are online know, we have about 3 people that have it installed out of about 8 or 9, and we have 2 people that are using the virtual desktop, and one other person that wasn't able to get it running initially. Okay, so first window that comes up is this kind of a introductory or browser window. This gives you an opportunity to take a look at your at files that you've used recently, stuff that may be in a default folder, and so on and so forth, and open data that you've been working with previously. A lot of people, this is kind of like when you open up Word and you get the opportunity to use a template or something like that. If you don't want to see this, you can just click "Don't show this" dialog box in the future, and when you say OK, it won't come up. I'm going to leave it on there just so I don't confuse people for now. But I can cancel this, and I can just go to the opening page for SPSS. Now this looks like a spreadsheet. Looks like a spreadsheet, feels like a spreadsheet, but it's not a spreadsheet. This is a way that we're going to have to display and organize data in SPSS. All it does is display the data. The vertical columns are variables, like first column could be first column. I got to turn this thing off. Let me get rid of this thing. Yeah, that's what do you call it? Yeah. The truth is out there, right? Exactly. Let me get rid of this. I'm not used to this because I'm usually teaching at the basement on over at Silberman, and you can't get a cell signal down there. So I'm not used to turning my phone off. Get this thing off. There we go. Okay. Okay, so in the columns, we're going to have variables. First column could be gender. Second column could be age. Third column might be something else. Fourth column might be blood sugar levels. Fifth column might be blood pressure, and so on and so forth. The rows represent subjects. The whatever the date, wherever the data is coming from. Like this might be a student. This might be a second student, third student, and so on and so forth. I'm going to open up some data just so we can see it. If I can find it, tell you what, I'll search for it over here. MC birth. Okay, let's see if I can't get it to open this one. Okay, this is a data file that has a lot of fields in it, that a lot of variables that we use quite a bit just for examples, just so that we get some practice.
You have access to that?
Yeah, I believe it was one of the files that are on week one. So the data files that are given as examples on week one, and you'll see it posted a number of times. Nope, hasn't opened it yet though. Tell you what I'm going to do. I'll try that again, except this time I'll drag it to the desktop, and I'll open it this way. Okay, one way you can open it is double click it. You know, it'll double click one of the data files. The data files have a PostScript .sav. Okay, so if you do get info on it, or you look at the properties on that, it just opened it. Right, made a liar out of me. I thought it wasn't going to open it. And, well, maybe not. I don't see the data. Okay. Oh no, it opened it second time. All right, so I'm going to open it this way. I go to File, Open, Data. We're opening a data file, a .sav file. And this is an ordinary, everyday SPSS file. I'm not transferring data from Excel or anything else. I'm just opening an SPSS file. Now, when I go in here, it went automatically to a file that's in my user area called Data. I could also go up to the desktop to the file I just copied up there. But there's a bunch of files in here. They're all SAV files. CAD test SAV, high school female SAV, NC birth SAV, so on and so forth. The reason why I only see SAV files right now is because if you look down here under file types, it says SPSS.SAV. Show me only SPSS files right now. If I want to see Excel files, I click on here and I say now show me only Excel files. And there's some other files on there that are Excel files. There's a number of other kinds of files that can be imported into SPSS. I could look at all of those. I could just go down here to show me all files. And that's all the files that are in that folder. Happen to be in that folder that called data on my computer. Okay, I'm going to go back to show me only the SAV files. And I'm going to open up that NC birth mod file. Okay, it's warning me. Remember that we had a little bit of debate over whether to install Unicode or local or something like that. So I wouldn't worry too much about that. I'm just going to say yes. It may give me a warning back here, but it should work okay. No, it didn't even bother to give me a warning. Okay, so here is our data file, right? So it's opened up, and it's opened up in a window, as I described, that lists all the data. Each one of these rows represents a person, okay? And this is birth data from North Carolina sometime in the 90s, I believe, some year in the 90s, okay? And this is 800 women who gave birth in the state of North Carolina, chosen randomly out of all the women that gave birth in that state that year. Okay, so I have plurality. Who knows what plurality means? That's the first column is plurality. I'll give you a hint. All you see there is mostly ones, maybe occasionally a two. Number of babies, right, in that birth. So twins would be a two. So that's why you see so many ones there. Say, okay, sex. Is that the sex of the mother? I don't think so, right? That's the gender of the infant, right? The birth, right? Next one is going to be M age, mother's age. It's not very descriptive, right? Mother's age, M age, right? We know since it's dealing with individual births in North Carolina, M age. Yeah, that must mean mother's age, right? Okay, next one is weeks. That's weeks of gestation, marital status, the race of the mother, whether or not the mother is Hispanic, the amount of weight gained, whether the mother is a smoker, whether the mother drank during pregnancy, and ounces and grams. Based on those ounces and grams, what do you think? Well, we already had weight gain somewhere else, right? That's the weight of the infant at birth, right? So we have a whole bunch of information here. The ethnicity of the mother, whether it was a premature birth or not, and so on and so forth. So now I can look into this. I can just look at this and see the individual data for each woman just by looking at each individual row. There's 800 women in this. So there's 800. If I scroll all the way down, you see there's 800 rows. Right? There you go, 800. So I can now use this data and evaluate this data. If I'm just looking at this, I can't tell the average age of the mother or the distribution of the ages of the mother just by looking at this column of 800 numbers. It doesn't really tell me that much, right? Because it's just too much to really evaluate just by looking at it. So that's where our basic descriptive statistics is going to help us out quite a bit. But before we get into that, this is where we see the actual data itself. If there's a problem here, like, the second woman here, we made a mistake. It wasn't 37 weeks, it was 38 weeks. If you need to go back in and edit the data, you can do it right in here. You can just click into that and change that number just like you would in Excel. Okay, but let's take a look at how this data is really stored here. If I go down here to the bottom, can you see all the way down at the bottom? There's a little tab down there that says variable view. Right now, we're in the data view. If I click that button, we go into the variable view. By clicking back and forth, I can switch between the variable view and the data view. I can also switch up here by saying, let's see, where is it? By going down here and toggling between the data view and the variable view. View data, view variables. So what you see when you get into the variable view is you don't see the data itself. You see a description of each one of the variables, right? But for instance, remember that first column? That first column was plurality, right? Number of babies that were born to that mother, right, during that birth. So let's see what that is. Well, that's a numeric variable. They gave us a lot of width for no decimal places, obviously, right? So what is it? Well, you can actually create a label. Whoops. I had everything highlighted. Yeah, that's why I did that. I just want to spread out this particular column. Okay, you could also create a label. A lot of times when you put data in, you won't have a label there. All you have is the variable name. Variable name plurality means something to public health people. It may not mean something to someone else that might be reading this data. So that label gives you the opportunity to put in a better description. One of the things that limits you on the variable name is it has to be only letters and numbers, no spaces, no special characters, right? And it has to start with a letter. So that limits you in terms of what you can use as a variable name in SPSS. But the label, you can put anything you want in there. So we've previously modified this, and we put in a label. We put in number of children born of the pregnancy, of that pregnancy. Right? So now, whenever you create a table, instead of using the word plurality, it's going to use that description. Okay? The other place where that's kind of handy is MAge. Remember, so that's not a very good description of what the data is. Instead of using MAge when you make your output, it's going to say age of the mother in years. Right? Something a lot more descriptive. That's going to make your charts and graphs and tables a lot more useful. So race of mother. Now, the other thing that happens here is that if I go back to the data view, one of the things that you see here is that, for instance, under sex, the gender of the baby, right, you see male and female. Well, the data that's really there, I'm going to turn off value. I'm going to unclick value labels. The data that's really there is ones and twos, right? So the actual data is only ones and twos. The way that SPS knows what one represents and what two represents is go to the variable view, look at gender, look at sex, and if I go over here, there's our label. If I go over here to values, If I click in there, I can bring up a table that says value labels. 1 equals male and 2 equals female. So even though the data that we put into that we entered was 1 or 2, we now told SPSS in this column, if you see a 1, it means male. If you see a 2, it means female. Okay, so you actually do that. That's called coding. You code the data so that SPSS can understand it. And for instance, if you look for marital status, okay, I click into values, and 1 is equal to married and 2 is equal to not married. So now SPS understands that. What kind of variables do you think that you would usually use something like that, where you would code a value? Would you do it for numerical variables? No, because numerical variables are just numbers on their own. You would only do it for categorical variables, nominal or categorical variables, right? Because those are the ones, and you'll notice if you go across here, SPSS, you can define in SPSS what's a nominal variable, what's a categorical variable. Weight gain during pregnancy, that's a numerical variable. SPSS calls that variable a scale or scale. Nominal for categories, scale for numerical data, and it also has ordinal up there, which will come up occasionally as we go forward. Okay, so for instance, another one of these would be alcohol during pregnancy. And 1, 0, the mother did not consume alcohol. 1, the mother did consume alcohol. You could leave it just 1s and 2s, but then when you create a chart, you're going to see a bar. Let's say you create a graph. For the graph, you'll see 1 is this high and 2 is this high, but it'll only have meaning to you. It won't have meaning to anybody else that reads it, because they won't know what that 1 and 2 represented. Okay. Now, what's the advantage of using 1 and 2 instead of just typing in mother drank or mother didn't drink? See, yeah, less typing for starters. Also, much less likely you will mistype, or that you'll type something the computer doesn't recognize correctly. So, as far as the computer is concerned, if you typed in mother smoked and you did it in caps, it'd be different than doing. It wouldn't see it as the same as doing it in lowercase letters, right? Or if you put an extra space in, it wouldn't recognize it. So it's much more efficient to abbreviate that by using a number or a letter or something like that, typically a number, and then defining what that number means in the variable view. So I'm going to go in here, and I'm going to say a long way to answer your question, right? Your question was, how do you get Excel data in here? But I wanted to make sure that we understood what we were looking at when we took a look at this. Okay, so I'm just gonna quickly show you a situation where this is valuable to us. I'm gonna say to myself, I want to know more about the average age of the women that are giving birth in North Carolina during this year. So I'm gonna go here to Analyze, Descriptive Statistics. I'm gonna go into Descriptives. And I'm going to say, well, we're looking at the age of the mother. I'm going to move it in there. I'm going to look into options here, and it's going to calculate the mean for me, the standard deviation, the variance I'll check off, the range, and so on and so forth. And I'm going to say continue. And I'm going to say, okay, see what I get. So now SPSS opens another window. That window is called an output window. Okay, it always creates an output window separate from your data file. If I wanted to quit right now and save this information, I would have to save both the output window and separately save the data window, or I would lose one or the other. Okay, so for the most part, you're not going to be sending me SPSS output windows if we're going to have an assignment or something like that. You're going to take that table, for instance, that you might want, and you might say copy. I hit Control C, just so you know, or Command C on the Mac, and you might open up Microsoft Word, and you might say in Microsoft Word, okay, let's paste that in here. Edit, paste. And there's the table that we just created. And so if you're creating a report for another course or something like that, you're creating a paper, you can take whatever graphics, whatever tables you create in SPSS, and you can paste them into a Word document. Then you can send anyone the Word document, and they can open it and read it. Now, for instance, in this particular case, notice it says age of mother in years. It doesn't say M age, which might not mean anything to anyone. It says what we asked it to. So it makes it more descriptive. So what's the average age? Mean age is 26.92, right? About 15, 20 years ago. I'll bet you the average age is older now, right? 26.92. What's the standard deviation? Is 6. Later on, we're going to understand better how the standard deviation describes the spread of the data, right? And it's going to be important to us. What else would be a good way for me to understand the distribution of this data? Anybody got any ideas what would be another good way for me to understand this distribution? Yeah, variance. Variance is just the standard deviation is just the square root of the standard deviation. The variance here is going to be like 36 or something like that because the standard deviation is 6. How about graphically, right? A histogram, right? Histogram would be, give us a much better idea what's going on here. Can I produce a histogram here? The answer to that is yes. Now, I'm going to go back to the data file. Most of the time, you don't have to. My menus change when I switch between the output window and the data file. Some versions of SPSS, you see the same menu. You don't have to really switch back and forth to do things. So I'm going to click on here on graphs. I'm a legacy. I'm old, so I'm going to use legacy dialogues. There's a lot of different ways you can do this. And I'm going to say, let's see, I want to produce a histogram. Okay, and what's the variable I want to use? I want to use the age of the mother. And for now, I'm not going to worry about identifying things, putting in titles. I'm going to play with that. I'm just going to say OK. What's going to pop up? The output window is going to pop up again. And there is our distribution of mothers' ages in North Carolina. So you can see how many mothers were above 40 on this graph. You can see it seems a little bimodal there, right? So a younger group and an older group, right? So good question. Maybe that's women tend to have first baby around that age and then maybe wait a few years and have second baby. Who knows what's going on there? But we can see the distribution now because it's much more obvious graphically than it is just by those numbers. Those other numbers are going to be really valuable to us later on. Now, what's another interesting things that we might want to take a look at? Let's take a look at the average weight of the baby that was born in North Carolina. Okay, so I'm going to go to Analyze. Let's see, Descriptive Statistics, Descriptives. And this time I'm going to say, take out the age of the mother, and let's put the, let's see, the weight gain of pregnancy, weight of the child in ounces. I'll use ounces. Okay, I'll click OK. Okay, so it comes up with the same table we had before. In this case, the average weight of the baby. Don't go away because I'm going to get to your question. Now, if you want, you can go and come back. Okay, I want to make sure I answer your question. Okay, so the average weight of babies born in North Carolina was 116 ounces. Okay, you guys can tell me but you know better whether that's normal or not. Now, what would be of interest about the weight of the birth weights of babies in North Carolina? We have some data in here about whether the mothers smoked or not, or whether they drank. It would be interesting now to be able to compare, separate the data, mothers who smoked, mothers who didn't smoke, and see if there was a difference in birth weight, or mothers who drank and mothers who didn't drink. We can do that. We go into Analyze, Descriptive Statistics, except this time, instead of going to Descriptives, I'm going to go down one more to Explore. Explore gives us a little bit more opportunity to look at the data in different ways. I'm going to put in the weight of the child during pregnancy, the weight of the child at birth in ounces. And in the factor list, I'm going to put whether or not the mother used alcohol during pregnancy. We looked at that before. It was like a 1 or a 2. I forget what they represent, but I don't need to remember because SPSS will remember for me because we identified that in SPSS. Okay, so I'm going to ask it to, it's going to calculate the statistics for me. That's already turned on. I'm going to also ask it to do histograms for me. It's also going to, by default, do box plots. You wouldn't be able to tell that by looking at it. It's going to do it anyway. Okay, and in fact, some of you that have started working on assignment 1 have already started playing with some of this stuff in a reduced data set. Okay, so I'm going to take a look at this now, and I forgot to actually tell it to do it. Descriptive Statistics, Explore, and I'm going to, let's see, weight gained, not the mother, we want the child, so I got to go down further. Weight of the child. Now I'm going to break it up into 2 groups. two groups are going to be based on whether the mother drank alcohol or not. Now, in here, it identifies how you break up the groups by asking you what the factor is going to be. And by factor, it means how you're going to break it up. Like, for instance, you take a number like 12 and you factor it, it's 3 times 4. You broke it up into the two groups. So I'm going to break it up into whether or not the mother used alcohol or not. I'm going to put that into the factor list. I'm going to check statistics are turned on. Yes. And plots, my histogram is got to turn it on again. Okay, and I'll click OK. Let's see what we get. This time we get much more extensive statistics, and it's broken up into two groups. What's the average weight of a child that was born to a mother who did not consume alcohol during pregnancy? 116 ounces, pretty close to the average we had before. How about a mother who did consume alcohol? Oh, look at that, 108 ounces. The average birth weight of babies to mothers who consumed alcohol was less than those that didn't consume alcohol. I mean, in general, that's considered a bad thing, right? So there we have some evidence for why you might not want to drink while you're. Now, there could be many other factors here we're not looking at. You know, they might consume alcohol because they're depressed. There might be a million other things, you know, reasons for that difference in weight gain, right? But at least we know that this is the case. Now, because I clicked give me a histogram, now I also have a histogram for the mothers, the weight of the child in ounces, mothers who didn't drink alcohol and mothers who did drink alcohol. Well, what's the problem here? What can you see here is happening here? Very few mothers drank alcohol, right? That's why I didn't get a very interesting graph. And that alerts me to the fact also, gee, I wonder if this is really valid. It's such a small sample of women that didn't drink alcohol, right? So there were only, how many women were involved here? There were 800 women, right? 800 women, 794 of them said they didn't drink alcohol, only 4, right? So you wouldn't have noticed that unless you looked at the histogram and realized, well, what happened? There's only 4 women in this study, right? So at any rate, so that's something interesting. You also get a box plot, so you can see the ranges of values here. And notice there's very few outliers up at the top. You don't see too many babies that weigh, 12 pounds. But you see a lot of premature births. So these ones at the bottom here that are outliers are all premature births. Okay, and this is the 4 women that were, and you can see the median is lower than the median for the general population. But the data is so skewed because it's a tiny sample. So let's answer that question. What if I got, a lot of times I'll be working in Excel because it's convenient. I have it on my computer at home. I don't have SPSS handy to work with. It's just easier for me to work with. I'm accumulating a lot of data, or even more often, somebody gives me data in that form in Excel. How do I get it into SPSS? Let's take a look at that. I'm going to just minimize these, get these out of the way. Okay, so let me get to a data file here. Data. I don't know if I got it in here. Textbook. Is an Excel data file. Actually, yeah, I want to show you the data before I actually go. I don't like that one. Let me go back here. SPSS, open, data. Now, where was I here? I was in session 8A. Now, I'm sure I can get into that data file. Okay. Drag that out here. Take a look at the data in there. I have a whole bunch of Excel files in here. Let's see. Let me get high school athletes. What's this stuff? Oh, here we go. Okay. I'm going to blow this up so you can see it. Okay. This is actually something called paired data. The columns here represent the reduction in cholesterol levels in people that ate cereal every day for a month or something like that, right? So person number one ate cornflakes for a month, and that's how much his cholesterol went down. Then he ate oat bran for a month. That's how much his cholesterol went down there. It's paired data, same person, after two different environments, right? You don't have to worry about that. Okay, I'm just going to look at it as just as sets of numbers. Variable A, variable B. We'll really get into the paired test stuff later on. You don't have to worry about that. In fact, you want to know something? I'm going to eliminate this one. Let's get rid of that. Okay, I'm going to say save as. This is Excel. I'm just saving this to my desktop so I can work with it. Okay, it's on my desktop now. What do we see here? We see the variable name in the top row, and then we see a bunch of numbers, right? How many actual pieces of data here? We got 14, right? Because it goes down to 15, but it doesn't start until 2. Now, let's say I want to analyze that. Now, imagine instead of 14 values, we have 1,400 values, right? Obviously, you're not going to want to just copy and paste all that information into Excel, into SPSS, if you want to use it to evaluate it, right? So instead, what you can do is I'm going to close this. Now, as it happens, the reason why I'm closing this is, there is a reason why I'm closing this. SPSS will not open a file or import a file that's open in another program. That's kind of a quirk of it, and almost any other program will do it, but SPSS won't do it. Okay, so I'm going to go into SPSS now again, and I'm going to say File, oops, cancel, File, Open, Data, right? And then a browser window is going to come up, and I'm going to navigate to my data. Click down here, and it's on my desktop, so I'm going to my desktop, and I don't see the data. Anybody remember why I don't see the data? I got to change it to file type to Excel, right? Okay, file types. Now all of a sudden I can see the data. And it was, anybody remember what it was called? Here, flakes, right? That's the data right there. So I'm going to click on that, say open. It's going to recognize that it's an Excel file. And it's going to tell me, for starters, that it reads data on sheet 1. Remember, Excel has multiple sheets, sheet 2, sheet 3. You could have more than one sheet. There's tabs at the bottom. So you're going to have actual pages on one file, different pages on one file. It says on sheet 1, there's data from A1 to A15. That's exactly what we would expect. If there's extraneous numbers buried in there, you'll see that something weird will come up instead, right? So now the other thing you'll see here is read the variable name from the first row of data. Well, a lot of times your Excel file will just have data in it. It won't have the variable name at the top row, right? So if it just has data in it, you don't want to check that, right? Because if you check that, it will take whatever's in the first row and use it as the variable name. And then it won't use that as data. So you lose data and you get the wrong variable. But in this case, there was a variable name, right? Yes, I should leave that checked, right? I'm going to say OK. And Excel takes that data, imports it into an SPSS file. And there's the data now in SPSS, right? So on it. Now, what is that data? I'm also, you know what I'm going to do? Make believe that there was another variable there called, let's see, gender. Okay, I'm going to go back here. And let's say that we had some 1s and we had some 2s. Oops. Right, what do you think the 1s and 2s, if it's gender is the variable name, what do you think 1s and 2s stand for? Yeah, male and female, right? Okay, so does SPSS at this stage know which one is male or female? No, we have to code it. We have to tell it. So I go into the variable view, and now you'll notice that for gender, over here, it says measure unknown. Doesn't know what that is. So I got to click in there and tell it it's nominal. It's a category, right? And now that I've told it a category, I can go over here to values, and I can click into values, and this box comes up. And now I can tell it that the value 1 represents male, and the value 2 represents female. Add, make sure you click add, and then say OK. So now if I go back to my data view, I still see 1s and 2s. Why do I still see 1s and 2s? I have to change the view, right? I haven't toggled the view on. I can go here and say, show me the value labels. And now you can see 1 and 2 represents minimum. You can toggle that on or off, doesn't matter. So now, in the first column, though, that's a numerical variable. So it should say a scalar. And actually, SPSS predicted that correctly. It shows a little ruler over there, scalar variable. So now, cornflakes, right? So, cornflake, spelled wrong, in fact, cornflake really doesn't convey to someone that might be looking at the graph what we're measuring here. And what it really is reduction in cholesterol. Okay? And gender is, I'm going to call it sex instead of gender here. Okay, male and female. Right? So now, instead of just putting cornflake and gender on a charter table, now it's going to use what's in that label. So I'm going to go back to my data view, and I'm going to say analyze, descriptive statistics, explore, and I'm going to say, let's see, my numerical variable goes into my dependence list, my factor, which is my categorical variable, because it's 2 groups, goes into my factor list. I want my statistics, and I want my plots, and want my histogram, and so on and so forth, and I want all this stuff. I'm going to say, okay, and it actually calculates it for us. Very little data here. But the average for males was 4.3. The average for females was 3.8. And this is our 2 histograms for males and females. And this is our box plots. Looks like males had a higher reduction in cholesterol levels than females did in our bogus data, which we just made up on the fly. So you see how quickly we can do this. And it's particularly useful because we can take data from many sources. I don't know if you remember noticing there all the different file types, database files, DBase4, SAS files, and so on and so forth. So we can pull in data from many, many different sources. Okay, let me look online. Does that answer your question on how to import the data from Excel? Did that help? If it didn't help, you can take the last 10 or 15 minutes when I post the video, you will be able to play it, stop, go back over it, and in fact, I'll make sure that the data file I just used is available to you so you can actually just mimic what I just did yourself. Even stroke by stroke, even keystroke by keystroke if you want to. Okay, so I think that'll help you do that. Yes?
So for the question 7, it says that you want us to basically all our input data.
I'm not going to be doing too much of that. What I want you to do, for instance, is right now, remember what I did with the Word file here? Right? Now, for instance, I'm going to go back to one of the output windows if I can get to it. There's another output window? Nope. Was that the only output window I had? I think it was. Yeah, I put everything into this output window. I want to go back here, and let's say I want this box plot right here. I'm going to say copy. Then I'm going to go into Word. Then I'm going to say paste. Oops, I didn't copy it. Okay, oops. Oh my goodness, what did I do there? I got a bug I have a bug in my version of SPSS. I reinstalled it, and I know what's wrong here. It's not letting me copy pictures. You should not have that problem. When you copy and paste, you'll be able to copy and paste actual charts and graphs and so on and so forth. So this is fighting me. What I could do, just so you know, if I were really stuck, it's a Mac, and on PC you kind of have the same thing. You have programs that allow you to capture a page or a selection of a page, like this. Copy. Okay, and then I can paste that into. I'm not going to save it. I'm just going to take Word, and I'm going to paste it in here. Okay, why is it fighting me now? Huh? You know what it is? The bug is actually keeping my computer from recognizing that window. So it's not even letting me cut and paste it. They're kind of weird. I have to fit. That's my problem on my computer. You should not have that problem. Okay. Normally I would just highlight that say copy, go to Word, and paste. So on the homework, what I'm asking you to do is when you do your exercise, copy and paste the Excel tape, the Excel, uh, that portion of the Excel, or upload the Excel file. And on SPSS, instead of uploading the output window to me, copy and paste the tables or charts or whatever it asks for into a Word document and upload the Word document. I'm asking you to do that. An SPSS, I'm asking you to do that for two reasons. Excel, pretty much any version of Excel will open an Excel file, your Excel file. SPSS can be a little funky. Different versions sometimes might not like other versions' output files. Right? They'll like the data files, don't like the output files so much. So in order to make sure that I can read your result, I'm asking you to put it into Word and then upload it. It's good practice anyway, because if you're ever going to send this data to anyone or use it in a report, you're going to have to copy out of SPSS output window anyway, right? So to make it useful to you, it's better you learn how to do that now too. You won't be doing that too much because unfortunately, there's 60 of you guys. So I got, there's 3 files I got to open. I got to open 180 files and read them on the first assignment. So I'm not going to be able to do that too much, right? So a lot of times you'll see a lot of the homeworks have like, number answers. I'll ask you to produce the graph and then give me an answer from it rather than ask you to upload it. But I'm asking you on exercise 1, I'm going to go through looking at them all because it's valuable for me to know that you have Excel working, that you have SPSS working at some point. And if you don't have it working, you're still having a problem with it, don't worry about it. I'm more concerned that we get through this and everybody gets it working, than really getting this done in the minimum amount of time. So that's really what I'm doing with assignment 1. So yeah, so a lot of those, the first 5 or 6 questions are numbers or multiple choice or something like that. The last 3 things are problems that you use Excel and either upload the Excel file that you produced or upload a Word document with whatever was in there that you had to copy in or something like that. Okay, so I'm going to have to, I have to be over at the other building, right? So I have to bail now. I would prefer much to stick around here and chat for a while and stuff like that. I usually try and get here a little early. So if you have the opportunity to get here a little early, maybe I can work individually with some of you guys on that. And this was a special session because I wanted to go over this particularly. Age adjustment, I wanted to expose it to you, so I was introducing new material. It was kind of an odd week. I'm trying to sync up, like our Monday classes didn't meet this week. We have biostat classes on Monday, so I want to keep them synced up so we're covering the same material for the semester. So this was kind of more week 1A, and they weren't even here. So I just want to give you an opportunity to see that age adjustment because I think it's going to be valuable to you in the future. Okie doke. Hey guys, is that okay? Let me see how the guys online are doing. Received an email saying that there's a problem with access to new students, and by Monday, virtual desktop should be working for new students by Monday. That's what somebody has filled me in here. Okay, they went to the help desk, and apparently there is an issue with some new students being able to use the virtual desktop, which is the free version of SPSS. But they're talking about it may be a